Yes, sir, if you want.
Ladies and gentlemen, it's my great honor to introduce our distinguished speaker, Professor Dumitru Baleanu. He is a highly respected researcher whose work has made a profound impact in the field of fractional calculus, control theory, mathematical physics, and dynamical systems. Professor Baleanu is well known for his pioneering contributions to fractional calculus and their wide-ranging applications in science and engineering. Beyond his research, Professor Baleanu has been a mentor and collaborator to countless scholars worldwide like me. He is joining me in welcoming Professor Dumitru Baleanu, and let us look forward to his insight to the talk. Dumitru, you have the microphone.
Thank you very much. I mean, it's a great pleasure to hear your voice and to hope to see you in person soon. Thank you very much for your nice words. First of all, I would like to thank the organizers of this conference, first conference, and you'll see the evolution of this nice conference in the future. I'm sure about it. Thank you to Professor Mehmet Yavuz and his wonderful team for inviting me and taking care of my sometimes advisors regarding this conference. Very successful conference. So I decided to present some open problems in fractional calculus because there are some confusions, in my opinion, regarding the modeling part, and it's better to clarify to see more viewpoints in order to uh, follow the best direction possible. I kindly invite you to send your best papers in the journal Progress in Fractional Differentiation Application. And if you accept that fractional calculus deal with the study of so-called fractional order integral derivative operators over there or complex domains in their application, then you consider the fractional calculus an applied field. It is an extension of meaning. Being an extension of meaning, there is no one type of fractional calculus. There are plenty because you extend the meaning not in one way, but in many equivalent ways. We started in 1695, you see all this story. So now we are after 330 years of fractional calculus, and still people are asking what is a fractional derivative, which is a meaningless question. My point is, if you can associate the fractional calculus with some big discoveries in science covered by experiments, those big discoveries in science are the Higgs field discovery reported by CERN, plug satellite observation of background radiation, and pentaquark discovered by CERN. These are top level discoveries. Where is the fractional calculus? How can we manage this fractional calculus to produce such big discoveries, if possible? Here we have a counterexample in string theory. When we try to unify the quantum physics with quantum gravity, there is a problem, and people at this open issue, big open issue in science, and they use so-called string theory. Instead of ordinary particles, then we have vibrational state of a string. So it's kind of not local. And despite of many applications to unification of quantum gravity with quantum physics, black holes, and so on, still we have a problem related to the experiments, related to complicated theory. So finally, the string theory, which was very promising at the beginning, was forgotten for a while. So I don't think this happened with fractional calculus, because fractional calculus is related to real world problems. And let me tell you some facts that we cannot deny in fractional calculus. The applications on brake system and Citroën and other cars in France, fractional control, fractron, and many other applications. So these applications cannot be denied. So fractional calculus is recognized. Fractional optimal control and fractional control in general was very powerful in 2000, 2014, something like this. After that, it's not powerful in writing papers, but it is very powerful in making real-world applications. Also, in viscoelasticity and many others, 100 fields, mathematical biology, bioengineering, and so on. Which fractional operators we have to use? This is the first issue. And the majority prefer Caputo, ABC, Caputo Fabrizio, and Hilfer, and others. So the question is, when you choose an operator, why did you choose it? Because each operator has advantage and disadvantage. For example, in the standard books of Orhan, Spanier, Samko, Kilbas, and Marichev, Miller, and Ross, and Ostalov, you'll find many problems solved, differential equations solved by replacing the classical with fractional, and find new solutions. And we are dealing with Riemann-Liouville mainly, until the book of Kodlumi, when together with Manardi they introduced Caputo derivative. Caputo derivative can be seen in the paper of Bola in Spanier, but not named like Caputo. You can see it like transformation, integration by parts of Riemann-Liouville. So these are some of the books. Some of them present theoretical aspects like Samko, Kilbas, Marichev. If you ask Samko, as I asked 20 years ago, how about the application of your equation or your theory? He said, don't ask me about application. I am a mathematician. So I present just the mathematically being correct. The rest belongs to engineers and applied people. In Orhan and Spanier, Orhan is from chemistry, Spanier mathematics. I met Orhan in 2004. There are many nice chemical models which can be applied in chemistry. So they started to apply fractional calculus to real world problem. Postaluk is the founder of Cron, and he concentrated on fractional control. Miller and Ross are very famous, were very famous in 70s, and Miller and Ross wrote this nice book that we know. Other books, the making fractional calculus in bioengineering, fractional calculus and ways in linear discrepancies. A book from Marsha Gagey, Yang Zhu, and Bruce West. Particularly, I recommend to students to read Fractional Calculus View of Complexity Tomorrow Science. It's an amazing book. And these are my books, together with Trujillo, Dietel, Scholars, together with Mustafa, late Professor Machado, and Law. We have one with Mir Hashemi regarding the symmetries of fractional differential equations, about Handbook of Fractional Calculus Applications, Volume 7 and 8, edited by late Professor Machado. Now, at the moment, people are saying that fractional calculus is a non-local field, so let's apply methods and technique from non-local field in modeling. The topic is very, very well known in about non-locality. So this book discovered the concepts and foundation of non-locality, including quantum entanglement and its application for space-time. You see, we have non-locality in quantum physics, quantum mechanics, and cosmology. The topic is approached differently depending on the specific scientific content. So we moving with some examples of this book. So because we don't have to create the impression that now we rediscover the non-locality. Non-locality is very well known concept. If you look to this existing book, Quantum Non-Locality and Relativity, Non-Locality in Quantum Physics, Effects of Non-Locality and Gravity in Quantum Theory, Infrared Non-Locality, Modification of General Relativity, Focus on Cosmological Non-Locality, Developing an Approach based on Modified General Relativity and Cosmological Scales. In continuum mechanics and applied mathematics, so we have many methods, mathematical methods, how to treat non-local model when local model fail to capture the small scale effect. So what I want to tell to our colleagues or friends, to our participants, is that this non-locality issue is very well known so far. Now we have to study it, not only by replacing and constructing a model. So here, step by step, what each book discuss, look, anomalous diffusion and fractal mechanics, or continuous physics, polar and non-local field theories. And you see how the book is explaining the non-local continuum just by very nice abstract. Non-local effects in fluid dynamics, particularly in study of turbulence. This is the book you see for turbulence, local and fractional calculus approach to modeling turbulence linking to fractional dynamics. You see, very nice applications. Summary of the books for engineers, for quantum physicists, and for applied mathematicians. So in our case, we are mainly applied mathematicians, and the mathematical techniques used for modeling non-local systems are different. We have to be adapted. Okay, we know Riemann-Liouville, derivative, integral, and the main problem of derivative acting on a constant is different from zero. So this is a big problem of Riemann-Liouville, and the one aim was to construct different type of fractional calculus based on different kernel in order to bypass this problem, which has implication in not using Riemann-Liouville for developing differential geometry, but we can use Riemann-Liouville to develop models on fractals. So here, the dual linear derivative that you know, Caputo derivative, 58 years old, Caputo derivative. This is the Caputo, 97 years old. He went to Turkey in 2008. Nobody knows him. In the room, everybody applied Caputo derivative, but he was unknown as a person. And only after he gave his speech, people were able to know him as a person. It's a very big name in fractional calculus and applications. And he introduces derivative. I don't want to comment more, but this is left and right Caputo derivative constructed from Riemann-Liouville derivative like in 1974, but he reached this formula from different aspects. Actually, Abel in 1823, Liouville in 1832, Caputo in 67, Zarbashyan and Sessian in 68. They come to the same picture of Caputo derivative, same formula in different limits, and that's why the Caputo derivative is very strong. And whatever initial conditions are not like in the classical case, although they look like, but Caputo derivative remains a very solid operator coming from here physics, from tautochrome problem. First come derivative of 1/2, but it contains G is a gravitational constant. It comes from Liouville 1832, famous article, integral from 0 to infinity, and comes from his perspective, which means linear models of dissipation, whose Q is almost frequency independent of. This formula 5 is Caputo derivative. Why I am presenting this? In order to understand for the students particularly, but also for other colleagues, that Caputo derivative is untouchable. Whatever some people are saying that, of course, each operator, even the classical operator, have some advantages and some disadvantages. We don't have to look in the absolute way. Another topic related to the future applications are discrete fractional calculus. Here we have a nice paper published in Chaos and a patent based on this. So you can use it in modeling, in cancer model, for example, or in application regarding information encryption. Now going to fractional modeling, we are in the stage that fractional optimal control from the engineering point of view is decreasing as theoretical importance, but remains a solid part of fractional calculus. Now everybody try to solve fractional modeling. Fractional modeling is very tricky as model in general. There is no absolute model. You cannot say that mine is the best and yours is the worst. So you see all these big theories like dynamics of point masses, theory of relativity, electromagnetic thermodynamics, statistics are considered well up to a point, and some model can be wrong after some points. A link between phenomena, reality, and mathematics can therefore be established after we have tested real data. It's impossible to define a precise mathematical definition or notion of model unless we don't have empirical we have data. So people are talking about fractional model. We are not talking about empirical model. In the theory of modeling, for the ones who taught the course like this, Giovanni Calavotti book or like Mark Mershev, mathematical modeling, they are talking also about empirical model. So here is the place where fractional calculus can interact, not only taking a model from the literature, replacing and found the result. Now, although as I told you, many standard high-level books are dealing with replacing and see what's going on about solution and predictability, this is not the real way. Here, the models, like mentioned in these two references, mine and Professor Ravi and Armesha particularly, ask a question, identify the modeling approach, formulate the model, solve the model, answer the initial question. So this is one of the problem in fractional calculus about fractional models to not only to construct a correct fractional model, but fulfilling all these steps. Very few people who enter into the lab or they saw some experimental data and they are applying this 5-step method. So that's why we have more parts in mathematics. We treat existence, uniqueness, stability, and so on. But the question is, ask the question first and then identify the modeling. You cannot present in a conference a model which is stochastic and fitted by dynamical models. It's impossible. Or dynamical model fits with stochastic. So then identify the modeling approach. A modeling approach cannot be one. Then formulate the model, then solve the model, then answer the question. So this is one of big issues because in modeling we have numerical methods, we have existence, uniqueness, stability, so we have experimental data, and we have prediction, and fitting and prediction. Now, the new trend is going into artificial neural network approach, artificial intelligence, machine learning, and so on. This is one of my papers from 2017. Artificial neural approach for solving fractional differential equation. And according to machine learning, deep learning, this data science is a situation nowadays with some trends. But you see that artificial intelligence is quite old. Now the application to fractional calculus is new. For example, AI, big data driving a renaissance of hardware development and investment, where these accelerators, near memory, new memory, in-memory compute, novel HPC, and applications of fractional calculus and real-world application in AI across different domains, where neural network models in biology, fractional calculus, enhanced neural network models used to simulate neural and brain functions. So mathematical biology is a fruitful field for applying fractional calculus. Real-world application of AI and fractional calculus, image processing and computer vision, fractional derivative-based age detection. These are new trends when you can apply bioinformatics and computation biology, modeling biological system, because we have, like I show in the abstract of the books, that deal with the non-locality in complex biological systems. We have memory effect and non-local interaction. Why fractional calculus in mathematical biology? You can find in these two books, making fractional calculus in bioengineering, and our book with the attempt of Scala Centro Hill. So let's give a very brief motivation on this paper. We have real data, 6 point. We have proposed model with classical version and proposed model with 0.68 mu parameter with fraction. Which one is better? You see, it is better the fraction one. How about all mathematical biology complex systems? Are all mathematical complex system in biology described by fractional calculus? Of course not. Of course, you can find counterexamples everywhere, but it doesn't mean that the fractional calculus is wrong, or mathematical or system in mathematical biology are wrong. So here there are sets of systems, not all of them. So always we can find counterexamples. But here in the nuclear magnetic resonance, this was the first paper about anomalous diffusion expressed through fractional differential character in the block-to equation. We have an aim. Our aim is to apply to NMR and to see why the fractional calculus model is better than the existing methods at the moment, since we don't have an absolute model, and we can say we are top of the top. So basically, this type of question is fractional calculus good for all models? It's without any meaning, even if you can force a local model to be a non-local one, particularly in quantum physics, quantum field theory. These theories are, for example, quantum field theory is a local one, and it is accepted by experiments in CERN, and the Higgs boson was introduced. Now some researchers started to talk that in CERN they discovered some non-local phenomena related to string theory. Let's see what will happen. The same for NMR. Same for NMR. This is the motivation of NMR. You see how motivation, many motivation we have related to diffusion in medicine, and this is the theory, classical theory. And this classical theory cannot be applied to some experiment in the field, not to all experiments, to some experiments. So how can you improve this model, let's see, or equation?
Sir
We
Dumitru, sorry for cutting you. You have 2 minutes left.
yes. Let me check. Yes. So here we put the correction factor tau for the having the same dimension. So again we have a problem, right? And we have the fraction order special Laplacian. And we solve it and we found the solution which was better than fractal model. For the future, what do we need? Some open problems, good numerical methods. We don't have yet. We apply, but we don't have yet. So this is one. For the fractional modeling, because everybody is in, we have to give a motivation, the fractional modeling, based on real data, not only based on mathematical model. Fractional calculus combination with AI also can be a solution to diversify the application of fractional calculus and finding better results. Singular, non-singular, and modify non-singular fractional operators is another solution for some problems, some models. This is in Caputo-Fabrizio, and this is the motivation of Caputo-Fabrizio with the exponential kernel, because we cannot apply local theory and fractional calculus based on power law kernel. So this is our definition in ABC, published in this paper in Thermal Science 2016, where the power law was replaced with Litter-Leffler. These are some papers together with Professor Jajarmi. This is a nice paper about anomalous diffusion, combining singular and non-singular, comparing. This is Prakhar operator, which combine singular and non-singular depending on the parameter. So we have this type of operators. This is about series representation and about classification of classes of operator, about generalized memory and hypercoding, and about Boltzmann. The idea of generalized fractional calculus is not new. It was done by Boltzmann in 1874, also 1884. So when you say about this, we have to take into account the Boltzmann and Sony. In this book, we have plenty of operators. If you, for the students, if you can find it, you can apply it to many problems. And particularly this book contains a comment about non-singular operators. We have a f of a equals to 0 at the interval, so we have an extra condition. So this creates problem for non-singular, and for a non-singular like Caputo-Fabrizio and ABC, we solve it by modifying the operator. First, in Caputo Fabrizio, we obtain formula 6, you see, starting from a less than 0. So started with non-singular, and then we obtain singular, and generally this is the case for all non-singular kernel. And in ABC we use the integration by part, and we modify the operator in formula 5, and these are some of the papers published on modified ABC operator with very good results, numerical and from applied point of view. This is one of the last, 2025, when we discussed the modified Mittag-Leffler kernel in Dirac, and we have the modification of Mittag-Leffler kernel with discrete fractional calculus. Now, summarizing, we are looking for better numerical solution. We are looking for new models. We are looking for singular and non-singular and modified non-singular operators in order to give better results. And finally, we use artificial intelligence and fractional calculus to improve, I hope, we hope, the existing solutions of fractional differential equation by constructing different, for example, artificial neural network. So the future belongs to fractional calculus. Non-local phenomena are very big, so some of them are explained in fractional calculus with power law operator, Mittag-Leffler kernel, Caputo-Fabrizio. Some of them cannot, so it doesn't matter this. So be optimistic, and thank you very much for listening to me.
Thank you, Dumitru, for your inspiring presentation. We sincerely appreciate your time and effort for sharing your valuable insights with us, which is a valuable videos to the future. Now, is there any question from Professor Dumitru Baleanu? Please ask. Anyone? Online presenting? No. Participants? No.
Mr.
Professor Jafari, raise the hand.
Yeah. Good afternoon, Prof. How are you?
Fine. How about you?
We are fine. Thank you. And thank you so much for your nice presentation. I don't have a question. Because your voice, we always be looking for the energy from you, but I don't know today. We cannot see also your picture. If no mind, at least switch on your camera. We see you. We miss you too much.
I tried, but I couldn't. Do it to have video. So I am trying to open now the video. You cannot start your video because it's disabled by the host. So that's why I cannot be seen by video. Not due to me.
Now you can open your video if you want.
Yes. Now it is open. Yeah, I can see myself. I think you can see me too. Can you see? Hussein, can you see?
Nice to see you.
Okay, now I am very sorry I was unable to attend in person in for the conference, but for the next, I'll attend sure, and I hope Mehmet Yavuz and his team will organize a second edition next year.
Dumitru, thank you again for your nice presentation.
Thank you.
We can close the session.
Thank you very much. Thank you.
See you. Bye.
Bye-bye.
Dumitru Hoca çıktı, şimdi çıkıyor. Merhabalar. Ha, o çıktıktan sonra mı yapalım? Ha, Dumitru belki oturumu da izlemek istiyordur. Ha. Nur Hoca'nın mikrofonu açmasını isteyeyim mi? Açtı.
Esteemed professors, colleagues, and participants, I'm glad to welcome you to the United Speaker Session 6 at ICMADS'25, where Professor Jorge Eduardo Macias is going to make his own speech. Thank you. It is raising an honor for us to have you here. Thank you for your kind consideration again, Professor Jorge.
Thank you. Thank you. Thank you very much.
Professor Diaz, invited speech is entitled on a fractional generalization of a nonlinear model in plasma physics and its numerical resolution via a multi-conservative and efficient scheme. As for his brief biography, Professor Diaz is a professor of applied mathematics at the School of Digital Technology in Tallinn University. Professor Diaz, PhD, is in mathematics from Tulane University of Lausanne and also in physics from the University of New Orleans. He has more than 200 journal articles on abstract algebra, nonlinear partial differential equations, mathematical and stochastic modeling, numerical analysis of differential equations, computer simulation of systems in physics, and fractional order calculus. Following this brief introduction, we can note that it's a pleasure and honor for us to invite Professor Diaz for his invited talk at our session. Over to you, please, Professor Diaz, if you are ready.
Yeah, I am ready. Can you see my screen?
Yes.
Okay. Yeah. Okay, great. So I'm ready, and if you're okay, I can start, Professor Caraca. So thank you very much for this nice presentation, and thanks for the invitation. I'm very happy to give this talk. This talk is based on a paper which was recently published in Journal of Computational and Applied Mathematics. The title is basically a fractional extension of a model in plasma physics and its numerical resolution. And beforehand, if you hear some dogs, I apologize. Okay, so my apologies. Okay, so this is basically the itinerary I'm going to cover. So it's pretty long, but I'm going to shorten it a lot because I have basically 20 minutes. So I'm going to start with the introduction. So the introduction, what I'm going to be talking about today is about the Sakharov-Rubenchik system, which is a system introduced.
Excuse me, we cannot see your presentation.
My apologies. I'm not sharing my presentation. Give me a second. I'll have to share screen. Am I sharing my screen now? You don't think so? Share entire screen. How about now?
Yes.
Okay, so you can see my screen now, I guess. Can you see it now?
Check.
So am I sharing my screen now or
Yes.
not? Okay,
Yes.
thank you very much.
Okay, thank you.
Okay, thank you very much. Okay, I apologize. So basically what I was telling you is I'm going to talk about the Saharov-Provenchik system. I'm sorry, which is a system, which was introduced in 1972 in the context of plasma physics. And this is important, it's in red. So this system conserves certain quantities, especially mass, energy, momentum, and a linear functional. We know a lot about the system, but we would like to extend it in this talk to the fractional case scenario. And to that end, I'm going to use Rist's fractional derivatives. This is my definition for Rist's fractional derivatives. I'm not going to go over it. Possibly Professor Baleanu already talked about this derivative. I'm going to fix a spatial domain D, which is an interval, and omega is my space-time domain. B is a complex function, and rho and u are going to be real functions. I'm going to have initial data. These are some parameters, and these conditions need to be satisfied in order for the system to have solutions. And finally, this is important, I'm going to consider orders of differentiation alpha and sigma between 1 and 2. I introduced some standard notation, inner products, P norms. We already know what they are. The reason I am using Rist's fractional derivatives is because this theorem, which is basically an extension of the theorem of integration by parts, is satisfied. And this is the system of partial differential equations. This is my fractional version of the Saharov-Provenchik system. You see there are 3 partial differential equations. They're nonlinear differential equations, and the coupling is really hard. We impose initial boundary conditions. And we must mention that this system satisfies, has associated some quantities, a mass density, which is given in this form. This is the total mass of the system. This is down here is the total energy of the system. We also have some total momentum associated and some linear functionals. Now, I would like to mention that these are my system, my fractional system is a fractional extension of the Saharov-Provenchik system. And these functionals are extended fractional functionals of the integer order functionals. What we would like to do in this work is to prove that these quantities are conserved. We would like to propose a numerical model. We would like to show that the numerical model conserves the quantities. We would like to show that the model is multi-consistent, stable, convergent, and we'd like to verify computationally all of these properties. Okay, let's talk about the conserved quantities for the continuous case scenario. So in this section, B, rho, and u are going to be functions that satisfy the fractional Saharov-Provenchik system. And here we just prove that the mass, the energy, and the momentum are conserved. So my first theorem is that the total mass of the system is conserved. And the idea is just to take the first derivative with respect to time of the mass, and eventually substitute the first equation, the first Saharov-Provenchik equation. In that way, you show that the derivative of m is equal to 0. Now, to prove that the energy is conserved is a little bit more complicated. You need to prove, first of all, certain formulas. So they are proved here. Okay, I don't go over the proofs because of the lack of time. And my theorem states that if sigma, the order of differentiation sigma is equal to 2, then the total energy of the system is conserved independently of the value of alpha. Okay, again, because of the time constraints, I'm not going to go over the proof, but the idea is to take the derivative of the energy with respect to time, use the lemmas, use the fractional Sakharov-Rubenchik system, and well, do lots of calculations. Okay. Finally, for the conservation of momentum, we also need various formulas that we need to establish first of all. Those are some of the formulas, those are the proofs. And the theorem states that indeed, if sigma is equal to 2 and alpha is between 1 and 2, then the momentum is conserved. And here I would like to call your attention to the fact that we are restricting to the case that sigma is equal to 2. Alpha, again, is any number between 1 and 2. Okay. And again, so for the proof, we need to take derivatives with respect to time. We need to use integration by parts extensively, the lemmas, and the Sakharov-Rubenchik equations in fractional form. As I said, the purpose of this talk is to establish a numerical method and analyze it to solve my system. So these are just standard conventions. I'm going to introduce partition norms, partitions, some discrete notation. So basically, the boldface letters are going to be numerical approximations. I introduce discrete operators, which are very standard nowadays. And this is something which is not standard. So the question is, how are we going to approximate fractional derivatives? And the way we're going to do that is by using fractional ordered center differences. This is not some contribution of mine. So they were proposed by a Portuguese mathematician called Ortigueira. He established that the fractional ordered center differences, which are here on the left-hand side of this equation, approximate Rist's fractional derivatives with second order of approximation. So I introduce more discrete operators. Okay, these are standard operators. I'm not going to go over them except for the first one. The first are fractional ordered center differences, but the others are standard operators. I introduced discrete inner products, discrete norms, and then I remember this theorem from the literature. So this theorem tells you that fractional ordered center differences actually satisfy a formula for integration by parts. And this is great because this is going to make the magic in the proofs of the next section. Okay. But before that, we need to propose the numerical model. So this is the numerical model, the discretized form of our system, and the initial boundary conditions. I'm not going to go over this because it's easier if we look at the stencil. This is the numerical stencil for my numerical method. As you can see, this is an implicit scheme, which has associated some density, some mass, energy, momentum, and the other functionals also. These are the discrete forms of the quantities, of those continuous quantities. This is the discrete total mass. This is the discrete total energy. This is the discrete total momentum down here. And these are the discrete linear functionals, which all of them are approximated at the time k, at the same time. I'm going to talk briefly about the structural properties. So basically, I would like to prove that these discrete quantities are conserved because in the continuous case scenario, they are conserved. Okay, and our study is partially successful. To establish the conservation of mass, firstly, I need to establish some formulas. So they're established in that lemma. And this theorem states that indeed the total mass of the system is conserved. So the way to do that is by taking the inner product of the first of the numerical equations with this quantity. Okay, and then you take the imaginary part. These are the calculations. I can give you the presentation and the paper later on if you want. But as you can see, the discrete mass is conserved throughout time down here. Okay, to establish the conservation of energy, you also need various formulas. So these are some properties that need to be established. Okay, those are the proofs. Okay, and then the theorem, it's the discrete version of that continuous theorem that I mentioned before. If sigma is equal to 2 and alpha is equal to 2, then the discrete energy is conserved. Okay, and to establish the energy conservation, we need to use the three equations in the numerical model. Now, conservation of momentum So here I would like to point out that conservation is in apostrophes, because really the momentum is not conserved. So you can see at property number 5 in this lemma. So there is an approximation here. So all the others are equations, but here this is just an approximate formula. So those formulas can be easily established. We need another lemma, an additional lemma. And finally, you prove that if sigma is equal to 2 and alpha is between 1 and 2, the momentum is approximately conserved. So this is one of the limitations of this study, and maybe I'm going to mention that at the end. So we could conserve all the other quantities except momentum. And also the linear quantities are conserved. So we're happy about that. Next, we would like to prove properties of consistency, stability, and convergence of the system. And I'm going to go really quick. I'm just going to give you the ideas. So these here are the differential operators in the Saharov-Rovenchik equations. And these are the difference operators. So they are the equations in our numerical model. Okay. For consistency, we need to compare them. So we need to compare each of the continuous formulas with the discrete formulas. And we see that there is a consistency of the second order. Moreover, so when we compare, for instance, the total mass of the system, the discrete and the continuous, there is also a consistency of the second order. Same thing for the energy, same thing for the momentum. So that's why we say that our numerical model is multi-consistent. Okay. And the proof is based essentially on Taylor's formula and the triangle inequality. For stability, we need a discrete form of Grunwald's inequality. So this is our discrete form. It's not mine. It was proved in 1977 by Penn-Yu. Okay. We need some lemmas to bound some terms. This is a huge lemma. Again, this is just to bound some terms. And this is stability. I'm sorry. This is where the proof of stability starts. So we need to consider two approximations for two different initial conditions, and we do some calculations. The theorem states that for sufficiently small tau, which is the temporal time step, the finite difference scheme is stable. Now, the idea of the proof, again, is to use Grunwald's inequality. So at the end, we need to use the Penn-Yu lemma. So this is the detail. These are the details on how to use the Penn-Yu lemma. Okay. As a corollary, we establish the uniqueness of the numerical solutions. And using a similar argument, we can establish this theorem, which is the theorem on convergence. So the theorem states that the numerical method is convergent of second order in the 2 norm. And finally, before I let you go, I would like to show you some simulations. So first of all, I'm going to use an exact solution, which is valid for the integer case scenario. So this is the exact solution, which is a soliton solution. And these are the solutions that we obtain using our numerical method. We do some analysis later on the convergence. These are just graph illustrations. The idea is that the numerical solutions agree with the exact solution. Here we are obtaining graphs for the mass, for the energy, for the momentum, and for one of the linear functionals, changing various values of alpha and sigma equal to 2. So you see, for any case, so these quantities are conserved throughout times. So this is in agreement with the theoretical. These are error quantities. So you see the errors in the mass and the energy are relatively small, not with the momentum, but this is okay because we showed that the momentum is approximately conserved. And these are errors for the other two functionals, which are pretty low from our point of view. These are studies of convergence in time. So I would like you to look at this column, the row column. you can see that indeed the rate of error is approximately equal to 2 in time, and same thing in space. So this is in agreement with the fact that our numerical model convergence with second order in both space and time. Okay. The question is, what happens if sigma is not equal to 2? Well, in the case of sigma not equal to 2, the numerical and continuous case results cannot guarantee that the quantities are conserved. And we can see that indeed, if sigma is not equal to 2, the energy, the momentum, and the linear quantities are not conserved. The mass is conserved, so this is in agreement with the qualitative and the theoretical results. Okay. And finally, some conclusions. I think I am in time. Yeah, I have 2 minutes. This is the first work in the literature which proposes a fractional version of the Saharov-Rovenchik equation and proves that the 5 quantities, it has 5 quantities which are conserved, proposes a numerical model to solve the continuous system, proves rigorously that the scheme preserves the quantities, proves mathematically that the scheme is multi-consistent, proves that the scheme is stable and convergent, verifies computationally the conservation of the quantities, and confirms computationally that the scheme is convergent. Now, this is a study, as I said, I'm going to mention, it was published, but there is a whole lot of things to do, and I wanted to mention some of those things to do, but I'm running out of time, and I don't want to miss this opportunity to thank Professor Yelis Karaka. She's a great mathematician and a great person, and I have the privilege of knowing her for some few months. Thank you, Professor Karaka, for this invitation. I also would like to thank the organization of the event. Also, I have a grant. I need to acknowledge this grant. And the results of this talk have been published in Journal of Computational and Applied Mathematics. These are my references. So the first reference is the paper I based this presentation on, and it was with Professor Siegfried Macias, also from my university. This is the paper by Ortigueira, where he studies fractional order center differences. The third one is by Peng-Yu. This is where I took the ground wall inequality. And this is the original paper by Saharov and Rovenchik, where they studied this system, not in the fractional form, in the integer order form. And finally, I'd like to thank you all for your attention. This is my information. In case that you want to contact me, I can send you the presentation and I can send you the paper happily. Thank you very much, Professor Karaka. I'm yours.
We thank Professor Diaz for his online invited talk presentation, in which he focused on the extension of the Zakharov-Rovenchik system to the fractional case by using these operators of fractional order in space. Thereby, this work proved the system is capable of preserving extensions of the mass, energy, momentum, and two linear functionals. As a novelty aspect, the work is the first report in literature where multi-conservative fractional expansion of the system is proposed, and a numerical scheme to approximate its solutions is designed and fully analyzed for conservative and numerical properties. We would be pleased if you would like to ask questions to Professor Diaz about the talk, please.
Kapatabiliriz.
From online, do you have any question?
Online'da yok.
Okay. Can I ask one question to please, Professor Diaz?
Yes.
Okay. Could you provide us some details about how the scaling properties of the fractional system differ from the classical or conventional one? I mean, I wonder if the fractional exponents introduce new types of similar solutions or wave dynamics to contribute to the model you have proposed. Thank you.
Yes, thank you very much. I cannot hear you. There is a lot of echo. Yelis, can you repeat your question, please?
Okay. I wonder if the fractional exponents introduce new types of similar solutions or
Okay.
valid
Yeah.
dynamics to contribute to the model you have
Yes.
proposed.
Okay.
Could
Okay.
you-
Okay,
Yes.
now I understand. Yes. So yeah, introducing the exponents, the differentiation exponents that you saw, sigma and alpha, doesn't lead us to the existence of soliton solutions. At least numerically, we checked if there were soliton solutions for this system. We couldn't find them, and that makes sense because, as you know, the differentiation orders, what they do is try to, I mean, they introduce a different type of diffusion. So one big difference between the solutions of the integer order system and the fractional order is that we lose soliton structures in this case. And I mean, that's understandable, but I don't know if I responded your question, Yelis.
Thank you. What could be the future directions and subsequent stages based on this research, like expanding this model?
I'm sorry, can you repeat again the question? Sorry, my apologies.
Regarding your study, what could be the future direction and subsequent stages based on this
Yes.
research? Expanding this model.
Okay. Yeah, so there are many other things that we can do. Look, see, one of the limitations of my paper is that we were not able to conserve the momentum theoretically. I mean, in the theory, you know, from the continuous point of view, the momentum is conserved, but my numerical model cannot conserve it. So this is one future possible direction of research to try to propose another numerical model in which the five quantities are conserved. So that's one of them, but there are many others. And if you want, we can talk about them. But this is, I think, that the most interesting one from the numerical point of view.
Thank you very much, Professor Diaz, for your interesting presentation and for your answers you have given to us. With this note, we can conclude our sessions. We extend our thanks to Professor Diaz and our participants for their contributions and attention. Enjoy the rest of the afternoon at the conference when we can proceed with the main events and parts. Thank you very much.
Thank you.
Aralarında oturmadık.
Güzel oldu işte. Çok iyi insan. Hiç kırmadı, hiç korktu. Çok güzel oldu. Teşekkür ederim.
Teşekkür ederim hocam.